Saxon Advanced Mathematics, lesson 89. We have, including this lesson, my students, a total of 8 more to go before spring break. I'm officially crossing this one off now. We're getting there. Lesson 89 is about the ellipse, part 2. Okay, so let's recap what we know about ellipses, which are just ovals, right? That's the fancy name for it. Okay, I'm going to draw you the 2 basic kinds of ellipses. They can go horizontally or they can go vertically. Please copy along with me. I'll make that one go out a little bit more. Don't drive yourself crazy trying to make them perfect, but just try to get the rough idea. This one's way better than this one, right? Okay, now we know that these 4 points have a really nice pattern to them. Oh, one thing I want to say is that we always associate the A value with what we call the major axis. So this point becomes A0, and this point is minus A0. But in this one, this point is 0A, and this point is 0 minus A. So we still have to keep track of our X and Y conventions, right? In just basic graphing. Nothing fancy about that. But in the horizontal ellipse, we use the A's here on the x-axis, and then we switch it here because this one's long and skinny. So that means that this has to be the B, 0B, 0, negative B, and this time it's B is here, right? Like so. And we also know that this value here is the same value as A, and this value here is the same value as B, right? And then the same thing here. This one is A, and this is B. Now we also have these, oh, and let me just show you the equations. We always associate the A with the major axis. So A goes with X in this example, and A goes with Y in this example. So we write Y squared over B squared plus, I'm sorry, I said Y, I think, but I meant X. It's like this. I wrote it correctly. Hi, Grace. She's back with a bone, a rawhide bone. She was just having snack time with her sisters in the kitchen. Good girl. She's going to lie on the couch and chew while we talk about ellipses. I mean, that sounds good, right? Okay, so this, we've all done this before. And you guys mastered this. It's been a while, though. It was a ways back. Just looking to see if John mentions what lesson that came from, but he doesn't. Okay, the other thing that he hasn't taught, that we have seen, but we didn't talk about a lot, is that somewhere about here, we put in what we call the focal points. Typically, we call them F1 and F2. And they're always on the major axis. Okay? We didn't use those for much last time. We just noted that they were there, that they determine where the major axis is. And we talked a little bit about this idea that if you imagine taking a bulletin board and putting this piece of paper over the top, if you took a short piece of string and tied it to 2 thumbtacks and pushed the thumbtacks in at the focal points, then what you could do is you could catch your pencil up in the edge of that string and pull it to its extreme length all the way around. And that defines the length of that piece of string, and these 2 focal points would define how big an ellipse you would get, okay? And John does a nice job of drawing those pictures here in the book. And we're going to be talking about this a little bit today. I'm not just going off on a tangent, although that's fun too. All right, so he's left out some of the details here, but it's like here are our 2 thumbtacks, our focal points, and here's our piece of string, and there's our pencil pulling, right? And what he's saying is notice that the distance on each side of the pencil is going to change as you pull the pencil around, right? But the total that they add up to will always remain the same. Yeah, that kind of makes sense, right? The string is the same string as you tug it around the focal points. So it makes sense that the D1 and the D2 are going to always add up to be the same total. Now, look what happens when you pull it all the way over to the side here, right? The pencil's gone all the way around. The string is now pulled taut from F2 all the way to the edge of the circle and then back to F1. Notice the interesting thing about the length of the string. If you mentally take the fact that there's a double string here and you add it to this side, you'll see that the length of the string is the length of the major axis. What? Look at that. Isn't that interesting? Now, okay, so the length of the string, the total length of the string is equal to the major axis. But now let's take our pencil back up in this picture. We take it back up to the top where the two distances of the string are exactly equal. That tells us that at this point, they're exactly equal to half the major axis because we determined that the string is equal to the full major axis. So when it's up here at half and half, the length of that hypotenuse, if you will, is equal to half the major axis, which is what we're already calling A. So A is the distance from the origin to the edge, the origin to the other edge, and the hypotenuse, or the distance from the focal point to the top, which is the hypotenuse of the triangle we're drawing there. Super, super useful and interesting. What we're going to do is we're going to put this fact to work now, and I'm going to draw this triangle on my paper. It's a triangle buried in I'm going to put it on the grid so that it's easier to see the whole thing. Okay, so if this is F1 and this is F2, we know that this whole dimension is A, but we also know that when we have our pencil up here, then we're dividing this line that's equal to this full length. We're dividing it in half. That means it's equal to that. That's really weird and not necessarily what we would have expected. Notice that this is equal to A. This is already equal to B. And so we can easily solve for one of these missing pieces. That's what we're going to work on. Here's my pencil holding this all in place. And here's the other part of the string, right? This is the string. String. Pencil. Do you guys ever use spirographs? This makes me channel a spirograph so hard. All right. So the distance from F1 to 0B up here, right, equals 1/2 of the major axis, and that's also equal to A. Okay, we're going to keep this in mind, and we're going to see how John uses this in a problem. I'm so excited, and I know you are too. Ready? I'm still in love with my book. It's got really smooth paper, and I like how it goes up high, and I'm so happy not to have the other kind of binding. I'm glad to be back to spirals. I got a nice set of these on Amazon that comes in all the colors of the Saxon books, because you know that's where my heart belongs. So I'm chuffed, like you don't even know. Write the standard form of the equation of the ellipse with vertices at... Okay, so these are the vertices at plus minus 5, 0, and foci, plural of focal points, at plus minus 4, 0. Okay, now we're going to start with a diagram. And this is super helpful to us because this is going to help us establish which way the angle goes. Because we know that the focal points, I'm going to use the bastardized plural. I'm not going to say foci because that sounds like focaccia bread and that just makes me hungry. Let's say focal points. This helps us figure out, are they on the x-axis or the y-axis, because that will determine which way we orient. And I see that this means they're on the x-axis, right? It's going to be like this. Oh, I don't really need to put arrowheads, but we'll just do that. Okay, so 1, 2, 3, 4. 1, 2, 3, 4. I'm just trying to make it proportional. The vertices are at plus and minus 5. Okay, so that means we have to go one more out, right? Because these are the focal points and they're inside of it. Now, what this problem does not tell us is how far B is. So we don't know, so I'm just drawing it. Oh, I did this wrong. Right? The circle, the ellipse, does not touch the focal point. That's within. I accidentally drew it touching the focal point, but it should be all the way out here at the vertices, right? So this is 5 and 0, and this is minus 5 and 0, and this point is, this is at 4, minus 4, and this is at positive 4. Okay, we're supposed to write the equation. Okay, let's look at what that's going to look like. We're going to have A associated with the x-axis. Okay, we know that A is equal to 5. We already figured that out, right? That we knew that right there. But we don't know what B is. I just kind of drew it in there, but I just guessed. I know it's less than 5, but I don't know what that number is. We have to figure it out. Well, here's the way we can do it now. We can take advantage of this fact that we figured out that this distance from here to here is also equal to A, right? Because this is 1/2 of the major axis. That's from that whole pencil in the string thing that we talked about a few minutes ago. We know that this line is equal to half the major axis. The major axis is 10, right? It goes from positive 5 to negative 5. So that means this, I'll redraw the triangle here so it's cleaner. This triangle right here that I'm drawing here, we know that this is 5. Okay, that's pretty cool. We also know that this dimension of it is 4, because that's how far it is out to the focal point, right? So now we need to find this side. Well, let's call it B because this is our B value that we need to square right down there, right? So now we can use Pythagorean, bless his little heart, to solve this. So these are the two legs. That's the hypotenuse. So I'm going to say 4 squared plus B squared equals 25 squared. This is 16, so I'll subtract 16. Oh, I'm sorry, 5 squared. I got excited, didn't I? That is indeed 25. This is 16. Sorry, I'm going fast. I hope you can keep up with this. B squared equals 25 minus 16. Oh, I love this one, right? We get B equals 3. All right? So now we know that this point is 0, 3, and this point is 0, minus 3, and we can rewrite this as x squared over 25 plus y squared over 9 equals 1, and yay, we got it right. Cute, right? Once we know this little trick about how to find the distance from the focal point up to the top here, and we know that that's equal to half the major axis, which is equal to A. it's not so bad. We should use a little Pythagorean and it's all good. All right, let's do it again with another example. There are 3, yes, 89.2. Scooch up a little bit. Write the standard form of the equation of the ellipse with vertices at 0 plus or minus 6 and the foci at 0 plus or minus 5. Now we're first going to draw our picture. When we think for just a second, we know that when the number comes second, that's the y-axis. So that tells us that this is going to be an up and down, a portrait style, a vertical ellipse. This one was horizontal landscape, all right? But we can just tell by the way these points are written, right? Here the value is in the x position. Here the value is in the y position. That's how we can tell. So I'm just going to mark these. I'm not going to try and measure it out like that. I'm just going to mark them. I'm going to call this 5. I'm going to call this 6. I'm going to call this minus 5. And I'm going to call this minus 6. And then this is a distance we don't know yet. My ellipse goes from the vertices, not from the focal point. Right? A little lumpy. It's getting closer. And I can draw a triangle. Now the question is, what's the easiest way to orient this triangle? John draws it down. I'm not sure that's really helpful. I don't need this mark there. Ignore that. I kind of like to always draw it in this quadrant, but I know I'm going to go from the focal point to here. I know that this equals half the distance of the major axis, which is 12. So I know that this is 6. Okay? I'm going to try not to draw a separate triangle this time. I'm going to try and keep it in here so that we can do it as succinctly as possible. I know that this dimension is 6. It's half the major axis. I know that this dimension is 5. I'll circle them so that we can tell they belong to the triangle. Because look, it shows right there my focal point is at positive 5. So this must be 5. So now we need to solve for this, and this will be equal to, this will be b. This, we know just by looking at it that a equals 6, right? Because that's that distance. So now we're going to solve for b. 6 is the hypotenuse. So I'm going to say, I'm going to do my squaring right away so I don't go crazy like I did last time. 25 plus b squared equals 36. Pythagorean theorem, jumping right into the squares. Subtract 25. B squared equals 11. So b equals the square root of 11. That's perfectly fine. We can use a value like that just fine. Don't let that radical sign freak you out. That tells us that this value is equal to the square root of 11, which is a little bigger than 3, right? Because 3 times 3 is 9. 4 times 4 is 16, so it's greater than 3 but less than 16. I like to think about that just to help me make sure this is reasonable. My calculation hasn't gone wonky. Because once I see it as a radical, I have to stop and think in order to visualize that number. But this is 3 point something or other, and given these other numbers, yeah, I would believe that. Okay, so now we have our b value and we're ready to write our final form. We know that a goes with the major axis, so a is going to go with y. So x squared is going to go with b squared. B squared is just 11 plus y squared over, what's our a? 6, so that's 36 equals 1. Yay, I got it right. I did the Algebra 2 lesson before this one. I usually go in order. I do 1/2, 1, 2, and then you guys last. It helps my brain just kind of come up to cruising altitude. In Algebra 2, so I was almost 3 lessons into my teaching for tonight, I said that 6 minus 3 was 6. I cannot imagine what must go through your head as students when you see me do something like that. It's like, what? And I caught it a few seconds later, but it's so funny to be in this and think, to be in this video format, right? I mean, if we were together, we would all just have a laugh and it would be over. But it's like there has to be this moment when everyone that watches it is just dumbstruck, like, what did she just say? And I'm like, oops, never mind. Okay, but the crazy hard things, it's so much easier for me to get right. I just make the silly little mindless mistakes sometimes. Don't we all, right? I kind of love when I do that because it's so important to know that everybody makes those goofy mistakes. There's no way to eliminate them. We just try to catch them. All right, a horizontal ellipse. Oh, thank you for telling us, John. Has a major axis of length 10. Okay. Major axis equals 10. And a minor axis of length 4. If its center is at the origin, thank you very much, find the coordinates of the foci and write the equation in standard form. Okay, we can do this. We know it's horizontal because John told us so. So let's just start sketching. I'm just going to draw it. Not bad. I'm better at my horizontals than my verticals always go too fast. Okay, the major axis is 10. That means A equals 5, right? So this point is 5, 0. This point is minus 5, 0. The minor axis is 4. That means B equals 2. Okay, so this is 0, 2, and this is 0, minus 2. I feel good about this so far, right? Okay, now let's put in our focal points. I'm just slapping them in there. I know they're on the inside. I know they're most of the way out. And I'm not going to distinguish between 1 and 2. They're both just focal points. Now I know that there's a cute little triangle I can draw that goes like that. I know that this is going to be equal to B, which is 2. And I know that this is going to be equal to half the major axis, which is 5. It's this same value, right? It always seems kind of weird. They don't necessarily look like they're the same, but they are. And now we need to find this value because that will tell us how far the focal point's out. So I'm going to call it F, just for fun. Sounds like I'm saying I'm calling it F for fun because fun starts with F, but I'm calling it F for fun because that's the focal point. Oh, it doesn't matter. Okay, Pythagorean. We're going to say that 4 plus F squared equals 25. And we're going to say F squared equals 21. And so we're going to say F equals the square root of 21. So that means that the points of the focal points are square root of 21, 0 for this one, right? And over here, negative square root of 21, 0. And then the equation, we've already got our A and B right here. We know that A goes with X. So we'll say X squared over 25 plus Y squared over 4 equals 1. This is the standard form of the standard form of the equation of the ellipse. Yay. So guess what? Did we get it right? Let me look. 25 over 4, 21, 0, negative square root of 21, 0. Yay, we got it all right. Okay. I hope this all sits firmly in your head. We have done so many different shapes, haven't we? We've learned so many weird and interesting things about different shapes and the form of their equations and how to calculate them. It's kind of fun, but at this point, a little mind-boggling. If you just understand this, even if you feel like you can't keep it straight from everything else, that's okay. Just stick with it. You're doing great. Lesson 89 is now complete. I now return you to your normal life. Thank you. Goodbye.